Hi, I'm Herb Gross, and welcome once again to Math as a Second Language video series, where today we're going to talk about a topic that truly shows the, so we say, the non-science part of mathematics, the liberal arts, the humanities part of mathematics by a concept called irrational numbers. Those are numbers, believe it or not, that cannot be expressed as the quotient of two whole numbers. And in the real world, you say, who really cares because we can round off? More mathematics has been devoted to irrational numbers than to the study of rational numbers. In other words, there are mathematicians who study mathematics for the same reason that poets write poetry. It's not to build a better technological world. It's not to build bombs. It's designed to show the growth that the human mind can soar to if properly trained. And that, to me, is the greatest thing that we can impart to our students, is the thing that they take with them through life is the ability to think logically, and a proper study of mathematics is one of the best vehicles. In fact, in my mind, it's the best vehicle I know of to help people improve their minds, okay? It's the calisthenics of the human mind, okay? So let me just show you why irrational numbers were called irrational. In fact, today, don't we talk about it, if something is a crazy thought, we say it's irrational? It's derived from something that happened historically. The ancient Greeks believed that rational numbers ended the number system. There couldn't be anything beyond rational numbers. And to show you why this was not so strange for them to believe, let me do an experiment with you. Let's suppose I take a line segment and I say divide it in half. I say, okay, now divide each half in half. Then I say, okay, now divide each of these pieces in half. Okay? And I can go on like this. I said, now divide each of these pieces in half. 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 Can you see what's happening? Can you see that eventually, if I keep doing this, the whole number line is going to be filled out? The amazing thing is, there's a difference between a dot and a point. Euclid in geometry defines a point as that which has no parts. Well, if it has no parts, how can you see it? See, this cannot be a point because I can take half of it away and still see it. We represent points which we can't draw by dots which we can draw. Let me show you what happens here mathematically. Let's suppose, just for the sake of argument, that line segment I picked, I'll call one of the endpoints 0 and the other endpoint 1. When I divided that line into two pieces, what was the name of this point? It was 1/2, wasn't it? If I divide each half into two equally sized pieces, what do I get? Fourths. If I divide each fourth into two equally sized pieces, I get eighths. If I divide the eighths into equally sized pieces, I get sixteenths. If I divided the sixteenths into equally sized pieces, I would get 30-seconds. You see what's by the time I fill in this line, which looks like it's filled in, the only fractions I've represented, the only points I've represented are points whose denominators are powers of 2. Halves, quarters, eighths, sixteenths. The question is, what happened to 1/3? I don't even have all the rational numbers here. I don't get 1/3 by doing this. And what happened was, the dot that I was using was so thick that when I drew it, it overlapped and included the point 1/3. Let me see if I can show you. I obviously did not draw this out because there'd be too many pieces here to look at. I computed this in advance. If you take 42 128ths and write that as a decimal, it's 0.328125, terminates, okay? And notice that that is less than 0.3333 endlessly. 43 out of 128 is 0.3359375, okay? Which is bigger than 0.3 endlessly, 3333. So in other words, what happens is the line that we were drawing was so thick that it covered both of these points. And in between was 1/3. In other words, if you do this experiment with your students, they'll all tell you that the number line is filled in. No, it's not. It's filled in only if we use dots, and a dot is not the same as a point. So it wasn't that strange that the ancient Greeks believed that all numbers were rational. The reason I like decimals, a main reason I like decimals, is that if we have to deal with irrational numbers, which come up in almost every math course on the more advanced level, we certainly don't need it on the elementary level, for the same reason that we don't need endless repeating decimals. We always round off. But let me show you in terms of decimals how we know that not only are they irrational numbers, but the irrational numbers actually dwarf the rational numbers. Look, 0.28 bar, see 28 with the bar over it, is rational. We just showed that. How would we write this? That was what we did the last lecture, okay? But this is a rational number because it's what? A repeating decimal. Let's suppose that as I write this decimal out, I decide I'm going to inject one more 8 every time I write the cycle. So in other words, this will be 0.2, 288, then 2 followed by 3 8s, then a 2 followed by 4 8s, then a 2 followed by 5 8s, etc. How can there possibly be a repeating cycle here? Because each time I'm adding one more 8 to the previous cycle. The cycle is changing each time I get to a new batch of 8s. So whatever this number is, it can't be a rational number because, well, why can't it be? Well, it doesn't repeat the same cycle of digits endlessly. See, in the previous 2 lectures, haven't we shown that a number is rational if and only if as a decimal it either terminates or repeats? Look how easy it is if you randomly were to write down a decimal, how easy it is to see that it's very unlikely you're ever going to get a rational number. Look, let's suppose I have a spinner, like the Wheel of Fortune. I have a spinner, and it has the digits 0 through 9 on it. And I'm going to now invent a decimal. I'm going to write down a 0 and a decimal point, and I'm going to spin the spinner. If the spinner comes up to be an 8, that will be my first decimal digit. I spin it again. If it turns out to be a 3, that will be my next decimal digit. If it turns out to be a 4, that will be my next decimal digit. And I keep on doing this. And here's the key thing. I'm going to do this forever. And the question I ask you, in your mind, try to visualize the answer to this. What is the likelihood that eventually, spinning the spinner at random, I'll ever get the same cycle of digits to repeat endlessly? Here I'm spinning this thing. You really believe that if I went on forever, that I will eventually get to a sequence of digits, just keeps repeating over and over again? Or will randomness tell me that that won't happen? In other words, it's very, very unlikely that I'm going to wind up with a repeating decimal by doing this, okay? So, in fact, it almost seems like there shouldn't be any rational numbers, because my intuition says, if I went on forever, I don't think it's possible that if I went on long enough, I'm going to just keep repeating the same cycle, especially unless this spinner is geared by some illegal device to always just keep giving me the same cycle of digits. In other words, it makes it almost seem like a miracle that there are even rational numbers when you look at it this way. So I think that's enough evidence to show that not only do irrational numbers exist, but they make the rational numbers look puny. And we're not going to pursue that in any more depth than this, but I did think I would like to show you a few examples in real life. What was the first hint that the Pythagoreans, the ancient Greeks, Pythagoreans, had that there must be irrational numbers? Well, they could geometrically represent a length that was the square root of 2. In other words, a number which when multiplied by itself would equal 2. And because they could represent that number by a geometric construction, they assumed it was a rational number. Well, it turns out that it's not a rational number. Now, again, in the real world, we don't care. See, what should the square root of 2 be? It's the number which when multiplied by itself would give me 2. Well, if I square 1.4, I get 1.96. That's too small. If I square 1.5, I get 2.25. That's too big. So I know that whatever the square root of 2 is, it's bigger than 1 and 4/10, but less than 1 and 5/10. And I could keep on going this way. And let's suppose that by some computation or other, I got to the stage where I showed that if I squared 1.414213, I got 1.999, etc. But if I squared 1.414214, I got 2.00284, etc. That would also tell me that the square root of 2 is more than this number, but less than this number. And so in the real world, I can pin this down as close as I want. I'll just keep taking approximation after approximation until I get to a place where I can't measure any more accurately because of the limitations of my measuring device. But here's what happens. Let me show you how they knew that the square root of 2 was irrational. If you square any number, the number of prime factors that the square will have will always be even. For example, suppose I took 2 times 3 times 7, that's 42, and I squared 42. My claim is that every prime factor, namely the 2, the 3, and the 7, would occur an even number of times. Why? Because I write it down twice. So if it appeared even an odd time here and an odd time here, when multiplied, that would become an even number. In other words, I started with a 2, a 3, and a 7. I square it. What do I have now? 2 2s, 2 3s, and 2 7s. See? In other words, I've multiplied this by itself. So the important thing is when you square a whole number, every prime factor occurs an even number of times. By the way, I'm not expecting you to internalize this in a way to explain it to your students. In many respects, this course is for you, not for your students. I'm trying to share with you what I think is important and why I think it's important. And your role is that wherever you agree with me, your role is simply to say, how do I transmit this to my students in an age-appropriate manner? So again, if you feel you don't need to use this for your students, that's fine. I'm just showing you historically the kind of logic that went into why we learn about prime numbers and the like. It's more than for finding common multiples. So the ancient Greek proof, there's several versions of it. I'll pick one that I think is the least complicated. Suppose the square root of 2 was rational. That means there would be a common fraction that would equal the square root of 2. So let's assume that the fraction in lowest terms has a numerator that will denote by m and a denominator that will denote by n. Okay? And so m over n is the square root of 2. So we'll square both sides. So the m times m becomes m squared, n times n becomes n squared. By definition, the square root of 2 times the square root of 2 is 2. So the square of m divided by the square of n would be 2. Get rid of the denominator by multiplying both sides by n squared, and you get m squared equals 2n squared. Now watch what happens. M is a whole number, and we squared it, which means that every prime factor occurs an even number of times. So in particular, the factor 2 will appear an even number of times. By the way, remember 0 is an even number, so even if m is not divisible by 2, the factor 2 appears an even number of times, namely 0 times. Let's look at 2n squared. N is a whole number, so 2 appears an even number of times. So if I multiply that by 2, since there was originally an even number of 2's, there's now an odd number of 2's. How can these two numbers be equal if when they're broken down into prime factors, this one has an even number of factors of 2, and this one has an odd number of factors of 2? So for whatever practical value there was, and maybe there was none, the ancient Greeks were able to prove that the square root of 2 was irrational, which caused several Pythagoreans, believe it or not, at least as history records it, to commit suicide because it was such a blow to their whole theory of the ideal universe. At any rate, there's another number that you might find interesting that's irrational, that you don't have to prove to your students is irrational. You know, all circles have the same shape. In other words, if I have two circles, say this one and this one, this is, by the way, this is a circle. This circle and this circle are obviously different sizes, but they have the same shape. So in other words, the ratio between the circumference of this circle and its diameter is the same as the ratio between the circumference and the diameter of this circle. In other words, even though this circumference is bigger than this and this diameter is bigger than this, the ratio is the same. Just like saying 3 is greater than 1 and 6 is greater than 2, but the ratio between 1 and 2 is the same as the ratio between 3 and 6. The numbers are different, but the ratio is the same. And because that ratio is the same, we give that a special name, and that number happens to be what you all remember as being what we call pi, the ratio between the circumference and diameter of a circle. It turns out that pi is irrational. We don't have to know the proof of that. It's quite advanced. And the first several digits of the decimal are 14159. Pi is 3.14159, then a whole bunch of digits, and it never will repeat the same cycle endlessly. Do you notice that in schools we often say, let pi be 3 1/4, or we'll say, let pi be 3 1/7? Notice that it can't be 3.14, because pi is 3.14 and then some. What this is really saying is, if you only care about accuracy to the nearest hundredth, then you can replace pi by 3.14, but it's not exactly right. In other words, you're going to get an error coming in here, but if you can't measure more accurately than this, that error won't show up. Other places say take pi to be 3 1/7. Remember what 1/7 was? It was the repeating cycle 142857. Again, what happens here? Is 3 1/7 exactly pi? No, they agree to the second decimal place. The ancient Egyptians took pi to be 3.1416. Okay? And that said what? If you're rounding off to 4 decimal place accuracy, this would be the right answer. And in fact, many ancient Egyptians thought that this was the square root of 10, because if you multiply 3.1416 by itself, it comes out very, very close to 10. These are just historical anecdotes that you can bring in to liven up a class period to point out how people thought back in a certain era and the like. But I think that's enough for today, which means we're now coming to our practice problem. And this practice problem is designed to show you that the irrational numbers are not closed with respect to addition. Namely, here's the problem. Is there an irrational number that we can add to another irrational number to produce a rational number? See, if you add 2 rational numbers, you can't get an irrational number. The question is, can I add 2 irrational numbers and get a rational number? That's what I want you to think about. Pause the video, think about that problem, come up with your own solution, and then come back, resume watching the video, and watch my approach to the solution. Let me show you one way of doing it. Earlier in our lesson, we showed that if you took 0.28, 288, 2888, and let me put like a little bar over this, a caret mark to indicate that each time I'm adding one more 8. That would be an irrational number. Suppose I took another number. See, 2 plus 7 is 9, 8 plus 1 is 9, 2 plus 7 is 9, 8 plus 1 is 9. Suppose I took another number, which I'll call m, and that will be 0.71, 711, 7111, etc. Okay, that's also an irrational number because I'm adding a 1 each time to the cycle over here. What happens when I add them up? I get 0.999999999, etc. And so these 2 irrational numbers would add up to 1. And if you don't like this particular number, I didn't have to pick this. I could have picked, let's see, N, M, I'll call the next one P. I could have started with, let's see, I could pick a 6 here and a 0 here. See why I'm doing that? Because now if I add them up, what will I get? 0.888888, etc. So in other words, I can take two irrational numbers and add them, get a rational number. In other words, the arithmetic of irrational numbers is not quite as pleasant as the arithmetic of rational numbers. In fact, once I introduce sign numbers, which we don't usually do, we may do this, maybe we will do this later in our course. But if I add a number to its opposite, by definition, the answer is always 0. So even if n was irrational, if I add it to itself, any number plus its opposite is 0. 0 is a rational number. 0 is the quotient of two numbers. You get it by dividing 0 by 3. You can divide 0 by 7. No matter what number you divide 0 by, you get 0. So 0 is a rational number. Okay? If I take the square root of 2 and add the opposite of the square root of 2, I get 0. By the way, just as an aside, the square root of 2 is irrational. I'll multiply it by itself. I'm multiplying an irrational by an irrational. What do I get? 2, which is a rational number. In other words, the irrationals aren't even closed with respect to multiplication. They're not closed with respect to division. Because if I divide the square root of 2 by itself, I get 1, which is a rational number. So again, can you see that even though there's no practical value to anybody who's outside of the field of mathematics, there's a great deal of stuff here that transcends what the human mind usually thinks in terms of. It's a growth process to allow you to assimilate thoughts that are beyond what you ordinarily thought you could absorb. At any rate, this concludes today's presentation. I'm looking forward to seeing you all next time. Until next time, have fun, be well.